In this segment, I want to talk about impulse. Impulse is an important idea. It's very closely related to the idea of momentum. The reason we like to talk about impulse is because it makes the connection between Newton's third law and conservation of momentum explicit. And so I mentioned that connection in my previous lecture, but using the idea of impulse, we can make that connection explicit. So what is impulse? Well, let's say that I want to change the motion of something. Well, what do I have to do to change the motion of something? Well, I have to push on it, right? So we've spent a lot of time talking about how pushes and pulls forces cause changes in motion, acceleration. So we've talked about that, but what we haven't talked about too much is the connection between how much change in motion we get and the amount of time that that force is applied, right? And so if I want to change the motion of an object, it's important what force I apply, certainly. We've talked a lot about that. But it also matters how long I apply that force for, which just makes sense, right? If I push on something for a very short amount of time, it's going to change its motion a small amount. If I apply that same force for a much longer amount of time, then it's going to change the motion of that object by more, right? It just kind of makes sense. And so impulse is this idea that sort of includes both of those things. It includes both force and the amount of time that that force is applied for. So let's imagine a scenario where I'm kicking a soccer ball. Right? And so here we see this kick, and we see, in this frame, the foot is just about to touch the ball. Here we see the foot is compressing the ball quite a lot, and so the force of the foot on the ball here is quite large. And in this frame here, we see the ball leaving the foot. The force is done. And so a fairly realistic graph of force versus time might look like this. It's sort of a Gaussian type shape, a bell curve, if you will. With that force increasing from the point of contact to the maximum point of compression, and then decreasing until finally the contact ends. And what we see here is this is sort of what we might call an impulsive type of a force. It's a very large magnitude for a short amount of time, right? 800 newtons, that's something like 200 pounds of force. That's a pretty large amount of force, right? But how long does it last for? Well, in this frame, we see it lasting for what? Oh, about 40 milliseconds, right? So it's a very large force for a short amount of time. How much impulse did the foot deliver to the ball? Well, impulse is something that combines both the force and the average amount and the time. And so I think the most accessible place to start with the idea of impulse is right here. Impulse, we use J to represent impulse, and it is a vector. I think the sort of most intuitively satisfying way to think about impulse is as the average force times the amount of time that it's applied for. And so again, it gives us this idea that the same force for a longer time will give us more change in motion, or to achieve the same change in motion over a shorter time, we need a greater force, right? It kind of makes sense, and this does capture that idea. Most forces, though, like this one from the kick of the football, right? They're really not constant. We've talked a lot about constant forces in this class, but finding constant forces in nature, it's a little bit hard. The weight is certainly a constant force that we see in nature. But other than that, it's pretty hard to find forces in nature that are truly, truly constant. And so this bell curve, this Gaussian shape here, might be pretty typical for an actual force. Well, what we could do is we could approximate that by a rectangle. And the rectangle here would have the average force as its height with the exact same duration for the time. And so that is how we would calculate the impulse using this equation here, the force average times delta t. Now, there's other ways to interpret that, and those of you who have had calculus will recognize the area under the force versus time graph as the integral of f dt. Now, we're not going to do integrals in this class, that's fine, but we do need to understand impulse as the area under the force versus time graph. And so that's what's being represented here. This is sort of a Gaussian shape, again, this curved shape, more realistic. The impulse is the total area under that curve. We could approximate that with this rectangle, right? So it's got the same exact area, but now we're doing an average force instead. This is the type of graph we'll more often see in this class. Or we could represent this also as a triangle, right? We could approximate this as a triangular force. So I won't ask you to do something like a shape like this, which would require some calculus. We'll deal with shapes that we can handle without doing calculus. Okay, so that's what impulse is. Now, what is its connection then to conservation of momentum? Well, let's look at a situation here. Let's say that I've got a situation where I've got some hockey puck moving along the ground. I'd say on frictionless ice. So this hockey puck is moving at some constant speed here to the right. And I take my hockey stick and I give it a little tap, and of course the hockey puck speeds up, right? No, nothing too surprising there. Well, let's analyze this situation and see what we can learn. We've learned a lot about forces, right? And so Newton's second law, set up as a cause and effect relationship, looks a lot like this. Again, I've just taken the m into the denominator here. If I was to talk about average forces, well, Newton's second law says the net force over m equals a, but if I'm only applying one force here, then my net force is just this force. And we'll say, you know what, in reality it might have some different shape. You know, it might be small in the beginning, peak, and then go off and then drop off again. But we're going to assume that it has a shape like this, okay? Some sort of a square shape. So, what do we have? We have that the F average divided by m is the acceleration. Well, we know that acceleration is final velocity minus initial velocity divided by delta t. Equating the two ends of this equation, we get this. And now notice I could cross multiply, bring my m over to the right side, bring my t over to the left side, and I would end up with this. Now, we have seen mass times velocity before, haven't we? Mass times velocity is the momentum. And so we see here that impulse is a change in momentum. And so we see here that forces cause changes in motion. We can think of that as a change in momentum. What's interesting here is that we could apply the same mathematics to the hockey stick, and we'd get the exact same thing, but with a negative sign. So whatever momentum the puck gained, the hockey stick lost. And that is how we get the conservation of momentum. So Newton's third law provides this connection with impulse between Newton's third law and conservation of momentum. Okay, so because impulse provides this connection, impulse connects a lot of different ideas that we've been talking about. Impulse can kind of take on a lot of different faces. And so I've made a slide here where we just kind of list off everything that momentum can be. We use J to represent impulse. We can represent that as the area under the force versus time graph, right? And so again, those are those shaded pink regions we were looking at in the previous slides. We can represent this as F average times delta t. Remember that J is a vector, and it's also the change in momentum. And so we can write it as delta mv. And often we'll end up applying momentum in this way. Impulse is equal to a change in momentum. So sort of equating the third and the fifth lines here. Okay, so again, impulse provides this important connection between a lot of different, pretty important ideas. Let's do a quick example. Two 1 kilogram stationary cue balls are struck by cue sticks. The cues exert the forces shown. Which ball has the greater final speed? Does ball 1 have the greater final speed? Does ball 2 have the greater final speed? Or do both balls have the same final speed? Why don't you pause the video, think about it, and I'll see you on the other side. Okay, so in this case, we want to think about impulse as the area under the curve. Why? Because they've given us some graphs of force versus time. And so maybe what we should think about here is impulse is equal to a change in mass times velocity. Well, of course, the mass of our balls are not changing. So then this is just mass times a change in velocity. Now, impulse in this situation, we should think about this as the area under the curve. And that equals m times my change in velocity. So let's compare the area under the curve. Here we have 10 milliseconds, right? These are rectangles, so area is base times height. 10 milliseconds times 100 newtons gives us something that's like 1,000 Newton milliseconds. The area here is 10 newtons times 100 milliseconds, also gives us 1,000 Newton milliseconds. So both figures have the exact same area. If that's the same, then they have the same change in momentum. Since they have the same masses, they have the same change in velocity. Both balls have the same final speed. How about this one? A 10-gram rubber ball and a 10-gram clay ball are each thrown at a wall with equal speeds. The rubber ball bounces back, the clay ball sticks. Which ball receives the greater impulse from the wall? And before you get too deep into this one, I'm going to go ahead and remind you that impulse is equal to a change in momentum. Okay, so what are we thinking here? Is it going to be the clay ball, the rubber ball, the same, or both zero? So the same and zero, or the same but not zero? So C would be the same but not zero, D would be the same but zero. Why don't you think about it? I will see you on the other side. Okay, well, this is interesting, right? Looking at the J side, we don't know F average, we don't know how long the ball was in contact with the wall, so I don't think we're going to be able to get too far by just directly calculating J. I think what we really want to do is calculate a change in impulse, or change in momentum, because they did give us enough information, not to calculate a number for that, but certainly enough information to compare it. And so, like many momentum problems, we're going to want to go ahead and do a before and after type of a picture, where the before and after will be before the bounce and after the bounce. So here's my wall, and here's my ball. And there's my lump of clay. So this is initially, right? And now my final picture looks like, well, my ball bounced off and is now heading in that direction. My lump of clay, however, stuck and has a velocity of 0. That's my final situation. Okay, well, what is our change in momentum? Let's see. Delta P is always, so for the ball, delta P is going to be P ball final minus P ball initial. And we have to be careful. Remember that these are vectors, right? And so what is the momentum of the ball in the final situation? Well, it's just m times v. Again, we don't know what m is, we don't know what v is. That's okay. That's the final momentum. What's the initial momentum? Well, it's m times negative v, right? Because it's going in that direction. And so what do we get? We get 2mv. Great. How about change in momentum for the clay? Well, that's the final momentum of the clay minus the initial momentum of the clay. Well, what is that? The final momentum of the clay is 0, and it had the same initial momentum. So what's the total change in momentum? Just m times v. So, which one has the greater impulse? Well, the greater impulse will be the object that has the greatest change in momentum. Which one has the greatest change in momentum? Definitely the ball, because it bounces. It's kind of a tricky thing. And it has to do with the vector nature of momentum. And I mentioned this in the other lecture, that momentum is one of those ideas that's fairly intuitive, and I find that students don't struggle with it too terribly much, except for the vector nature of it, right? That vector nature, the fact that the direction is matters, that's a little bit tricky. That is one thing that your intuition probably didn't bring into this class that you'll have to practice thinking about in order to wrap your brain around. Okay, so again, I showed this slide in my previous momentum lecture, but impulse provides this way of getting from Newton's third law to the conservation of momentum. These balls are about to run into each other, they have some collision, and therefore they bounce off of each other. Now, during the collision, Newton's third law is true, that F2 on 1 is equal to F1 on 2. Newton's third law says those forces are always equal and opposite. Furthermore, that time for interaction is the same, right? Ball 2 has to push on ball 1 for the exact same amount of time that ball 1 pushes on ball 2. Since they have the same force for the same amount of time on each other, but just in opposite directions, the impulse delivered to ball 2 is the negative of the impulse delivered to ball 1. Therefore, the change in momentum of ball 1 is the negative of the change in momentum of ball 2. In other words, any momentum that ball 1 lost, ball 2 picked up, and the total momentum of the system is conserved.